Hi, welcome everyone. So, today we will look into one of the most general problems we have in lot of domains known as text summarization. So, text summarization is a very wide domain grade problem and that involves problems that involve multiple applications. First, one of the main applications in text summarization is probably say you have a 1 hour customer care call and you want to summarize it. It may span from summarizing a text or a word file to a summarizing a PDF, summarizing a word with combination of PDFs, then CSVs and whatnot. Overall, this is a complex task and it involves a lot of think through insight when you actually solve this problem. This is a part of a deep learning, generative AI, and natural language processing course. So, we'll be looking into perspective what we can do to do best text summarization and get best summarization scores out of a given input or out of a given text. We have different approaches. At the end of it, we'll go through multiple implementations of the text summarization, starting from extractive summary to an abstractive summary using various LLM models. We will using an approach where we will start from a bit simpler approach and then move on to further tuning the complex transformer based encoder decoder models or sequence to sequence based models to get our results. We will be looking into various performance efficient fine tuning techniques, uh, also looking in to how to detect hallucinations and different aspects of avoiding or giving a false proof, a true response from the models. Okay, so let's get started. I will just start with my whole approach or ideology of how we will solve the problem, and then we'll see the implementation. So the problem statement here is we want to build a model that generates concise coherent summaries of long documents. Okay, and this is to ensure the summaries retain key information without distorting the meaning. Try various approaches of summarization like abstractive and extractive. We'll come to all of these technological acronyms in a bit, but just to give you an idea, there are multiple strategies one can apply to do summarization, and abstractive and extractive are two ways to do that. We'll be trying different data sets to ensure that we generalize the solution, and then we'll capture all the statistics and the metrics to make sure that our model performs well. Why this problem matters, as I explained, there is massive text around, right? We need to do automatic summarization. Summarization improves information access, decision making, and search, right? um, Specifically, we will follow abstractive summarization. That is a bit challenging because that requires the model to paraphrase, provide factual consistency, and long document handling. Okay, and we'll compare that with the state of the art models right now, like GPT, Gemini, and others, and see how the whole comparison goes. We have employed a technique called PEFT, performance efficient fine tuning of models, that leverages the concept of low rank segregation of the base models. So we will be using two different models here to demonstrate you the summarization, and that will be basically based on PEFT approach of training. Okay, so this is a short gist of the approaches, right? What we'll be doing, so we'll be looking into what an extractive summarization is, what an abstractive summarization is. We will be training without PEFT, we'll be training with PEFT, and then we will do the hallucination analysis, which is very important when we use large language models, because model may start faking basis on what data it has, right? You can see in the right there is a mind map of how the project has been modeled. So it uses two models, T5, which was developed by Google, and BART, that was developed by Meta. and basically these both are encoder decoder transformer based models. We have used multiple data sets, like especially CNN daily dataset to train the model, and also used XM dataset that will be used in the abstractive style summarization. We have used the as we explained, we have tried to implement PEFT, performance efficient, parameter efficient fine tuning, and inside that we have used low rank adaptation, in which we will see that basically the whole lot of millions of parameters can be compressed down to a small set of parameters, and then you can train easily on a lower compute machine. So, what is extractive summarization? You can see on your screen, extractive summarization is basically a way to a way to basically summarize a given paragraph into smaller chunks, or into a summarized chunk that is basically ranked in order. So you have a given paragraph, a big paragraph, and if I rank the whole paragraph into some sentences that has more weightage, or that is more you can say have the factual meaning related to the sentence, we will just rate it higher, and then print that as part of summary. That is called extractive summarization. Obviously it is very similar to implement, because you are just extracting the sentences out. It is grammatically correct because you are not interferencing with the grammar of the sentence. It is mostly an extractive sentence of the paragraph. It is great for factual summaries, right? You can because you are getting facts from the paragraphs itself, so there is no manipulation around it. But the whole idea is the semanticity is not it is basically no, it is just an extraction and not semantically classified or semantically summarized, and no new language is generated. It is limited to the material, and it is very less flexible. Similarly, in an abstractive summarization, abstractive summarization is basically, generates new sentences by understanding and paraphrasing the content. So it will be creating a new sentence out of the given sentences what you have. It is more fluent and natural, and it can compress ideas, enforce implicit meaning which is not explicit when you read the paragraphs, and rephrases for clarity as well. Obviously the challenges here is it will use a large language model which has a lot of parameters, and it is computationally expensive to train and requires a lot of data to train for your specific downstream tasks. There is a risk of hallucination that is associated to it. So basically whenever your model trains, it can start faking data, which we'll see, and how we can address those as part of of our project. And it is obviously a complex project to implement as compared to the extractive summarization. So I said we have used two models here. One is BART and one is T5. Both are encoder, decoder, and transformer based models. So BART, as I said, was both were actually developed contemporarily, and one was developed by Google and one was developed by Meta, Facebook then. And we'll go through the BART. So BART is basically, it combines bidirectional encoder and auto regressive decoder, right? So it combines a bidirectional encoder and auto regressive decoder. So it is an encoder decoder model in itself. Encoder captures global context from the entire article, and decoder generates coherent, well structured summaries. Okay, so the encoder's responsibility is to capture the global context from the entire article, and decoder generates coherent, well structured summaries. For encoder decoder to process the data together, cross attention mechanism plays a critical role. We know that cross attention is required from a decoder to encoder to understand the semantics of what the encoder is, and then auto regressively process the token by token output into the from the decoder. The mechanism allows decoder to focus on different parts of encoded output and ensures decoder produces coherent output. So the coherence of the output is maintained when we follow the BART model for no fine tuning onto the summarization tasks. In T5, all NLP tasks are formulated as text to text, text output enabling a single consistent architecture. The encoder model input context, while the decoder generates output using cross attention for coherent sequence generation. Simple textual prompts are required here to give and be explicit about what needs to be done onto T5. We know that T5 base offers strong state of the art results across benchmarks with reasonable computational efficiency. Okay, now we'll go to a very important aspect of how to train these language models or large language models with millions and billions of parameters over a local compute. As the compute is very low or limited in nature, basically there is a need to investigate opportunities or options wherein these language models or large language models can be trained on to some limited set of parameters and not millions and billions. So one of the techniques inside PEFT or performance parameter efficient fine tuning is LoRa, that is low rank adaptation of large language models. This is the paper. I have attached the snap of the paper here that basically talks about the LoRa, how it is implemented and whatnot. So what it does, so basically, as I said, when you have millions of parameters, it is essential to be thinking through of important parameters that is required for your downstream tasks. Here our task is summarization, and we know that not all parameters used in large language models would be responsible or would be committed to do the summarization tasks. So the idea here is that we take our pre-trained weights, whatever it is there, it is we freeze them and then we use a subset of those weights and we compress them to a lower rank, and then again bring it back to the same dimension when we actually need to work on the inference, and then both of them combined together acts as the downstream inference parameters. So just to give you an idea, just to say, so if you have 1,000 parameters in the large language models, only 1 to 2% will be actually trained on using LoRa rather than using the full model weights, which can prove very costly and effectively impossible to train on a local compute. It takes low memory, right? There are some parameters which we'll see when we look into the implementation and the code. One is the rank, so that depends, that basically defines the size of the trainable LoRa matrix. Alpha, that is a scalable factor. LoRa dropout, that is the probability or the percentage of which the LoRa will be dropping those of the percentage whatever you specify here. Okay, so how does it work inside the transformers, right? So when we actually think of a transformer architecture, right from the multi-head attention to the layer normal layer to the feed forward to the stack of these layers again and again, the main or major of the work is getting done inside the feed forward. We know that, and the major parameters of that are residing there. That is the neural network, what we actually have that does most of the tasks that an LLM does. So what it does basically, what we do is basically we attach the LoRa related parameters into the feed forward network, which has a freeze set of parameters what we have, and when combining both these parameters, we are able to perform better on the downstream tasks, because when we train our data set, when we actually train this model on our local data set or the downstream data set, this LoRa parameters get trained effectively, so that it learns what to respond and what to do when an actual inference is done at the runtime. So it freezes the original transformer weights to avoid the full model updates, add a small low rank trainable matrices which we call as LoRa adapters, then applies adapters to self attention and cross attention projection layers, that is query, key, value and objects, while keeping them frozen. So those will be frozen, and then dramatically, when you do all this will dramatically reduces the memory and compute for task specific fine tuning. Then when as I said, no LLMs are perfect, right? There is always a risk or probability to get hallucinated responses, right? One way to check for summarization type of task is to use LLM as a judge. When you use LLM as a judge, you have to configure another LLM that will be working on your summaries and just prove that these summaries make sense with respect to paragraph, but that would be a 2x of a work, right? One LLM to generate the summary and one LLM to validate whether your output makes sense or are actually related to the ground truth. So there is a paper. There was a paper that was published related to hallucination analysis methodology that is called as Hallu-Tree. Okay, so Hallu-Tree analyzes factual hallucinations in abstractive summaries. What we do, right? So and that does by decomposing them into atomic factual claims. So I will just explain the diagram you see on the screen here, right? So this is the model. The red one or the orangish one is the where my mouse pointed is. This is the model generated claim or the summary. You can see that it has generated two sentences out of the source, which is this one is the ground truth, which has been actually used to generate the summary for. Then what it does in a tree format, it takes all the sentences one by one and does the subclaim extractive analysis. And after doing the subclaim extractive analysis, what it does it from the sentence, it tries to see if the meaning or the actually the sentence was derived from the source. Okay, and it does that for all of the different nodes what can be possible in the summary from the source, and at the end of it it creates a tree, and basis on the reasoning trace of whether that fact is true or false, it says that the claim or the summary that has been generated by the model is actually a hallucinated response or a non-hallucinated response. It uses natural language interface. Obviously it is again using some lightweight model to actually do this inference, but again it is not like a full LLM what you see generally to do the actual which actually use all the weights and all the parameters to do the final inferencing whether it is a hallucinated response or not. And this is very important. As I said, it applies NLI style reasoning to validate every claim against the original article, and this makes your model more robust and your summaries more effective, so that users get a very real time and lightweight analysis, real time summaries as good as human summaries generated from normal humans. So we have used T5 small, T5 base. We have used LoRa, low rank adaptation, as I said, as performance parameter fine tuning approach. We have used different approaches, and we have created multiple time pipelines to try and validate on the different type of approaches or different type of strategies what can be possible on these two models, especially T5 and BART. We have used multiple data sets, as I said, and we have trained in different epochs. The CNN daily data set is the primary data set, and then we have used XM data set as well to just prove that it works on all different data sets. There are different experimental challenges when we do that. One is training loop hangs. Then there are object out of memory errors, right? Out of memory errors, extremely large training times, as you know that training text as we grow, no, the training can be directly proportional to the compute and the time what it takes to train the model. So LoRa and batch size tuning were required to stabilize the training. As I said, we have played around with different parameters what is there in LLM to make sure that we use the optimized batch size and the efficient LoRa parameters to train the model well. There can be multiple strategies again from here, like you can use multiple casual LLMs, decoder only model LLMs, other variants of transformer, sequence to sequence models, and you can also tune and optimize the different layers of transformers for better output and results. So these can be the next steps going from here. These are some of the matrices what we have got, right? So we used multiple types of model, multiple types of a given transformer model. So T5 small, T5 base, T5 base with different data set, and then BART base with PEFT. So we have used PEFT and others, to optimize the model training approach. And you can see the rogue 1, rogue 2, and rogue L scores have started beating the trend shows that the model rogue 1, rogue 2, and rogue 3 and rogue L scores are trying to beat the lead 3 significantly. And obviously this has been done on a limited data set, and there is definitely a provision, or we can definitely leverage this on a large data set to be more accurate and be more close to the state of the art models. The BERT score, which is the semantic scoring of the summarization, is, you can see, is 88.32 45 small, because it has been trained on 30,000 samples, which is significantly good as compared to the lead 3 of CNNDM. Okay, and this overall trend shows that, training more with more compute, and with full model training, this can be improved to more close to the state of the art models. This is what I explained, I think. So this is one of the demo inputs and output summaries. Okay, so you will see the faithfulness score being green for all of the summaries. We will show this into the Python notebook as well, and this is one of the snaps taken from there. And let's go to the coding implementation. So, and I will share my GitHub all these different implementations onto the video link and the LinkedIn post, so be tuned on to that. So we'll go one by one. So this is the extractive abstractive summary no comparison, how these both are used. So extractive summarization is being done through that spacey model. So these are very straightforward models which I have used here, and for abstractive I have used the T5. So let's go into, you can read into, I have already gone through it in the slide, and these are the text what we were just listening on. So we'll go through the code one by one. So this is the text. So we have taken a text, and then I have imported. So if you have not done downloading, you can download spacey. Okay, and then basically, import spacey and take out the stop words, which we'll be using in for our summarization below. And then you can also take this punctuation, import punctuation into the context. So you can see here this model I have used. So spacey.load encore web sm. Okay, and then we have started processing. So first of all, we have divided that into tokens. You can see here the whole text has been broken down into tokens. And then after taking the tokens, we will apply or remove the stop words, right? Take into consideration of having the impact of stop words and not having the stop words. Not all projects or not all texts are worth removing the stop words, so you have to consider both of the approaches into action. But generally it is found that removing stop words makes the summarization a bit faster. Then it has no then we have calculated the word frequency, right? Where each word will be passed on with a frequency, how many words that particular word exists in the sentence, and then basis on the max word existence, basically we have created a frequency probability of each of the word. And once we have done that, I think we will try to create an abstractive as well as the extractive summarization. So you can see here, after the tokenization, we have got this as a sentence, right? So it has tried to pick on basis on the probability distribution it has calculated, right? It has tried to take the highest probability distribution, and it is trying to take on the consideration of the highest probability distributed sentence, and it is trying to pick up basis on that score. That is what the extractive summarization is meant for. Similarly, when you actually do the LLM summarization, right? We'll just go through that. So it is basically a transformer model, right? T5, and we will be using T5 base here to summarize. So I have just taken the T5 base model, right? And will with the default T5 base tokenizer, and once that gets loaded, you can directly call the transformer onto a text, right? You can call the summarizer, and once your text passes through that summarizer, it will be basically returning on to the response. I've tried to build a small app here, but it is not rendering at this point in time. But you can definitely try to reload and try to see if you can render this GUI that is able to display the summary well. I will just no with the so these are the different approaches we have tried. I will just explain one by one. So one is the BART base, okay, with PEFT, what do we call as perform parameter efficient fine tuning. Then we have T5 base with PEFT. This is BART base. Remember this. This is very clear from the title of the path, title of the collab, and then it is T5 base PEFT, then T5 small PEFT, T5 base no PEFT n beams, and then T5 small PEFT. Okay, and this has the code to the different aspects of hallucination detection that we called as the hallu tree. Let's go into one of them. I will probably choose first of all PEFT, one PEFT in detail. Let's go in detail, and then we'll look into the last, which is the hallu tree section. Okay. So here you can see that initially we have installed the transformer, right? We have installed bits and bytes, which is required for PEFT, and then we have also installed we have the sentence piece, which is required for the parameter fine tuning. Then we have imported some of the libraries like OS random re numpy and ptorch, and then we have also loaded the dataset what is needed to train the model. From transport you can see we have in transformers we have imported auto tokenizer, auto model for sequence to sequence lm, and then sequence to sequence training arguments, data collector to training to sequence to sequence, and so on. So we have to just so first of all, as we know that we have to specify the model name, then you have to use the different arguments of your train val and test sample. So I have used here 30,000 samples here, 5,000 validation sample, and 500 is the test sample. This is what my distribution is about the training. And max input length is 512 and max target length is 64. Batch size, epochs, and learning rate has been configured here. Output directory and seed, it has been mentioned so that no models can be checked out at specific times to just make sure that no this happens. The checkout on the model keeps on happening after each epoch. So this is the shuffling of the dataset, which is required for randomization and normalization of the training dataset, so that you can take the non-biased samples from the model. And this is, it is important to know just randomly shuffle all your dataset before doing any task over to your model. Then we have the auto tokenizer from pre-trained model. So I think I have a valid output collab. Let me try to find it out. So we'll go in here and then we'll go on to let's see if it yeah, so let's go through it, because I think that particular stuff is not showing the output. You can still run it and see the output, but this is more of is associated with output, so I will just consider it from here. So you can see here we have already gone through it. The output is clearly being shown here, what output it is spilling out. With the interest of time, I cannot run it because it will be an hour long video, and it is very hard to know do all the things online. Sometimes it gets stuck into the debugging mode for quite some time, so it is important that we respect time, and you can just leverage this GitLab repo, right, which I will attach onto the video to explore more on each of the pipelines. So each of the pipelines has been uploaded here. These are the different pipelines which I have created, that gives you fair bit of insights into the developed process. So you can see here from auto trained, from p trained we have used T5 base, right, and we have used some LoRa config here. This is the PEFT config, right? Right. I was talking about rank, right? Alpha, and then we have to use no dropout and all those. So you have to configure all your LoRa config here, and once you run that, basically you can just click on the training. You have to attach a TPU or a GPU, right? And this is the check where you actually generally apply to check whether you are being using your TPU GPUs as part of your training. Once you define the sequence to sequence trainer, right, you will train it on onto your different epochs, right? Once that training completes, you can just start inferencing and see how the model summary looks. So this is the article, right, which is being passed as an input. This is the reference summary of the CNN daily, and this is the generated summary from the model. Okay, and yeah, and we have compared that with lead 3. So lead 3 is basically a summary that takes the first three important sentences of the summary and then compare that with your model. And once your model beats that statistic, so you can see the rogue scores get generated after your model training, and the rogue scores get generated for the lead 3, and you compare both of them, and if your lead scores are beaten by the trained model, you are all good. Yeah, so I think this is it. You will find more details of it into the GitHub. Okay, all of them are have been tested and they have been working. This is again an experiment. You For making it production grade, you will need to apply some refinements, analysis. You need to know go through some or automate. You need to create some automated pipeline so that these things work best for your use case and your downstream tasks. So as I said, summarization can be of multiple types, and you will have to find out the pattern what you need to summarize for, and you can choose one of these strategies, or you can imply some other strategy as well. A lot you can find on Hugging Face, a lot of experiments and other models that can do a specific type of summarization or task summarization basis on your need. I hope you find this useful. Okay. Thank you for being connected, and we'll come with a new project soon. Thank you.